Okay, class, where we are now is to talk about the collecting duct. The collecting duct is termed this because it collects modified filtrate. It collects modified filtrate from several nephrons. The reason I call it modified filtrate is because, remember, you get the filtration, but then you modify it with reabsorption and secretion. So this collecting duct right here is collecting from several nephrons. That's what these little nibblings are right there. Several nephrons, just like this one is. See? From several nephrons that would come in to this collecting duct. Okay. It travels straight down through the medulla of the kidney through a hyperosmotic area. So right in here, outside the collecting duct, is a hyperosmotic area. Why? Because this long loop of Henle did that. Now we're going to talk about that a little later. So what I just spoke of, that hyperosmotic area outside, sets the stage for the concentration of urine. The collecting duct is impermeable to water and solute unless hormones, particularly ADH, make it permeable. What they do is to stick in the aquaporins 2. The aquaporins 2 are the ones that are put in under homeostasis. It, like the DCT, distal convoluted tubule, has principal cells and intercalated cells. Okay? So we're going to talk about a little later the countercurrent multiplier system, and this has to do with concentration of the urine. Okay? So when the collecting duct comes down from here, it's collected from several nephrons. Remember, collected from several nephrons. Then what the nephrons do, what the collecting duct does, shall I say, come together and join in with several other collecting ducts to form the papillary duct. Then the papillary ducts open at the renal papillae, and then urine now drips into this. You say, why do I say urine? Because the minute you drip from here into the minor calyx, there's no more modification. Whatever it is, it is. Whatever it is, it is. And so it drips into there and then follows on down. Okay? So that's all I'm going to say about the collecting duct for now until we actually talk about concentration of the urine. All right, you can look at the summary yourself on your own. I'm not going to go through all that. So my next issue is the juxtaglomerular apparatus. The juxtaglomerular apparatus is an apparatus next to the glomerulus. It does a lot of stuff. It in fact is where the renin system comes in. The renin. Remember we talked about that in the blood vessels. Go back and restudy. The renin system is going to come in. So now we're looking at this juxtaglomerular apparatus. The juxtaglomerular apparatus, come here. The juxtaglomerular apparatus is actually made up of two things. It's made up of what we call juxtaglomerular cells, which are cells in the afferent arteriole. These are special epithelial cells in the afferent arteriole. Sometimes it's in the efferent, and some people have it in both. But most of the time it's in the afferent arteriole, these cells. And a spot of dense cells in the distal convoluted tubule. The distal convoluted tubule. And they come together and touch. Now let me kind of show you how this thing goes here. Strange as it might be, we come here and here is the distal convoluted tubule. The distal convoluted tubule comes and actually touches right next to these arterioles, afferent and efferent. And it's that touching, those two, with those specialized cells, juxtaglomerular cells in the afferent arteriole, and macula densa, specialized taller cuboidal cells in the distal convoluted tubule that touch and make up the juxtaglomerular apparatus. So that's what you're looking at. That's what you're seeing here. That's what you're seeing there. Okay? So that, in fact, is the juxtaglomerular apparatus. All right, now let's talk on it. Let's talk on it now. Okay. Arterial walls have the juxtaglomerular cells, enlarged smooth muscle cells. And I said epithelial. I should have said smooth muscle. Enlarged smooth muscle cells. So scratch that. I said epithelial, but smooth muscle cells have secretory granules containing renin. They act as mechanoreceptors, we'll see in a moment. They act as mechanoreceptors. So again, smooth muscle cells, I said enlarged epithelial, but smooth muscle cells. That would mean in the tunica media. I just want to clarify that. The macula densa, though, are in fact epithelial cells. Tall, closely packed distal. They're kind of tall cuboidal cells. They lie adjacent to the juxtaglomerular cells. And they're going to act as chemoreceptors or osmoreceptors. I'm not really worried about the mesangial cells. Okay, so let's go back. The smooth muscle cells are going to act as mechanoreceptors. I'll show you in a moment. The macula densa cells are going to check out chemicals and osmotic pressure. Okay? And like I said, the mesangial cells are just cells interspersed between there. They do several things: phagocytosis, contractile properties. And so, I'm not to say they're not important, but these others are very important. Okay, so that's why I kind of mentioned these here in the mesangial cells. You can glance at them, but I'm not going to really get heavy on those. I want to get to the heart of the matter for you all. All right, so that's the structure, and we looked at the structure already. All right, so I come back here now. Okay, this is where we kind of get, okay, the kidney needs to try to maintain an adequate glomerular filtration rate. So listen to me. We said that the glomerular filtration rate normally is about 125 milliliters a minute. That's what we kind of came up with. Okay, 125. Now, a lot of it depends on the blood pressure and other things, because remember, we said that you came, by the time you got to the down to the kidneys, down to the afferent arteriole, you were about a 55 mean arterial pressure, whereas in a regular capillary, you're about a 35. We said somewhere in that range. And we said that you had a 45 in opposing force in the what? In the renal corpuscle. So you had to be about a 55 to be above it and have 10 as a net filtration pressure. Now that meant if the blood pressure out of the heart dropped, because see, we're coming out with about 100 out of the heart, going through resistors, and we're saying by the time it gets to that afferent arteriole, it's 55. But if you come out less from the heart, think about it, then that means it's going to be less at the afferent arteriole. So that meant that anytime shock would occur, or if you had temporary hypotension, not to the level of shock, that you would lose the kidneys. So there had to be some internal mechanisms within the kidney to try to maintain a GFR despite fluctuations in the blood pressure. Okay? Now, if the GFR is too high, let's say your blood pressure is too high or there's too much flow, then needed substances cannot be absorbed quickly enough. I kind of brought that up before. Because it would be traveling too fast. Remember where I brought it up when I was talking about glucose? I said if you flow through that proximal convoluted tubule too fast, you can't reabsorb all the glucose, and some will be in the urine. Okay? That's just using glucose, for example. Then if the GFR is too low, everything is reabsorbed, and if it's too low, you don't get anything. Okay? So you have to adjust for that. All right. Now, There are three mechanisms to do that. So we want to evaluate these intrinsic controls, but the first thing I want to do is to evaluate how the juxtaglomerular apparatus works it. Okay?